All gas turbine engines use high-energy igniter units, or HEIUs, for engine starting. We'll investigate the intricacies of the high-energy igniter unit later. All gas turbine engines have a dual ignition system fitted, which means that they have two high-energy igniter units. The high-energy igniter units each feed a separate igniter plug. High-energy ignition systems have an output of approximately 12 joules. It may sometimes be necessary, to help prevent engine flameout, to have the ignition system selected in circumstances other than engine starting. For instance, during takeoff from contaminated runways, or flight through heavy precipitation. The use of the high-energy ignition system on these occasions will cause the igniter plug to erode so quickly that it will shorten its working life dramatically. To minimize erosion of the igniter plugs, some aircraft engines are fitted with a combination ignition system, which includes a low-energy, 3 to 6 joules, continuous selection, as well as the high-energy, 6 to 12 joules, starting selection. Continuous ignition, which energizes the low-energy mode of the igniters, is usually activated by selection of the appropriate switch on the engine start panel. The starting ignition system is activated when the engine start sequence is initiated, either automatically or by the operation of the high-pressure fuel cock, start lever, or fuel and ignition switch. The igniters are automatically deactivated at some point after self-sustaining speed, usually by the operation of a speed switch incorporated in the high-pressure compressor RPM indicator system. Some aircraft have an automatic ignition system. If an aircraft stall is detected, the aircraft stall warning system will automatically select the continuous ignition system. The high-energy ignition unit works on the principle of charging up a very large capacitor and then discharging it across the face of an igniter plug. The size of the capacitor makes it a potentially lethal device, and several safety factors have to be built into the high-energy ignition unit so that it conforms to safety regulations. This diagram shows the high-energy ignition unit mounted on the side of an engine and also the position of the igniter within the combustion chamber. The circuit shown here illustrates all of the components within a high-energy ignition unit, which is supplied by 28 volts direct current. With the supply connected, the primary coil and the trembler mechanism are fed with 28 volts direct current. The trembler mechanism works on the same principle as that of an electric bell. By doing so, it causes the primary coil input to become a sawtooth waveform. This sawtooth waveform is a very crude form of alternating current. Because we've generated alternating current, we can use a transformer to boost the voltage in the primary coil to 25,000 volts in its secondary coil. The 25,000 volts alternating current is changed back to direct current in the rectifiers. The direct current commences charging the reservoir capacitor. As the value of the charge in the reservoir capacitor builds up, it eventually reaches a level that causes a spark to jump the discharge gap. The discharge gap exists within an evacuated tube. The fact that the tube is evacuated means that changing conditions of humidity and altitude will have no effect on the voltage required to jump the gap within the tube. Consequently, the power of the spark at the igniter plug will be constant, regardless of ambient conditions. The electrical energy which has crossed the discharge gap has then to flow through the choke. The choke acts as an inductance and slows down the current flow. Slowing the rate of current flow makes the duration of the spark longer. The energy then passes to the igniter in the combustion chamber. If the unit has to be removed from the engine for servicing, any charge which may remain in the capacitor, even after the electrical power to the unit has been disconnected, could be lethal to anyone touching the casing of the high-energy igniter unit. The discharge resistors act as a safety device. by allowing energy trapped in the capacitor to leak away to Earth once the supply has been removed. The safety resistors act as a kind of safety valve if the igniter plug becomes disconnected. If the igniter plug did become disconnected, energy would continue to build up in the capacitor. The build-up of energy in the capacitor would eventually cause it to explode. To safeguard against a potentially engine-disabling explosion, the safety resistors allow energy in excess of the normal level to flow through them in an attempt to balance the charge on the plates of the capacitor. The normal spark output rate of the high-energy ignition unit is between 60 to 100 sparks per minute. However, the production of sparks is completely random, and if relight is selected with the aircraft on the ground, anyone listening at the jet pipe before engine start should hear an unsynchronized beat if both units on the engine are working correctly. As well as the direct current high-energy ignition unit, there are transistorized high-energy ignition devices. For aircraft which have an alternating current electrical system, there are units which will work on that supply. There are two types of igniter plug. The older of these two types works in a similar manner to that of the piston engine spark plug, but it has a much bigger spark gap. The potential required to jump this gap is approximately 25,000 volts. This extremely high potential requires very good insulation standards, both within the unit and in the cabling to the igniter. A more modern version of the igniter plug is the surface discharge igniter plug shown here. The end of the insulator of the surface discharge igniter plug is formed from a semiconductor material. The semiconductor material allows an electrical leakage to occur between the hot electrode to the body of the igniter. The electrical leakage ionizes the surface of the semiconductor material, which provides a relatively low resistance path for the energy stored in the capacitor. The discharge takes the form of a high-intensity flashover from the hot electrode to the body of the igniter, which only requires approximately 2,000 volts. This concludes the lesson on ignition systems.